Very good. We're all here, such as we are. Bless you. And a little housekeeping note. I anticipate I will. I didn't get a chance to process. I scanned the things, but I didn't look over them or process them, the exam. So I'll have that undoubtedly be doing that or probably posting scores on over the weekend, I would anticipate. I'm not overly engaged with the Super Bowl. I'll have plenty of time. No rooting interest. It's not a lot of fun. I'm in like a pool with squares. You buy a square, and that at least it'll keep my interest to some extent. Nevertheless, off we go. So I wanted to today we finish up, and we don't have a great deal left to do with the methods of control, and particularly the end of the chemical methods of control, and then we would then effectively we start the next unit, which is comparatively short, but for whatever reason, students find it the most difficult of this second exam. The second exam focuses on methods of control, the chemical aspects, and interestingly enough, virology. So probably the bulk of the next exam is forthcoming, and that's virology. You're going to see, and so the least part is the genetics, which we're coming up to. So that's really the introductory nugget here. I will. I'll have to upload some PowerPoints that I'm going to use, and some resources uh, vis-a-vis the genetics aspect. But for the time being, let's continue on with this. And this is kind of where we left off. And phenols are interesting, if nothing else, historically, because this is, and I had to, they didn't have the L in that, this is the substance that Lister used. And phenol has been around for a very, very long time. And yes, it has an unpleasant odor and irritates the skin. In very high concentrations, it's carbolic acid. Interestingly, from a chemistry perspective, it's a weak acid but a strong base called the conjugate base for you chemistry fans. That's what does the damage. And we've used it forever to cauterize things. Okay, I've used it clinically to cauterize things for years in its concentrated form. But when you dilute it, it undergoes interesting changes. When you dilute it sufficiently, it's really a useful antiseptic. When you dilute it, not quite so much. You can even use that when people are allergic to local anesthetics, which is very, very interesting. That are there, and like most of them, it doesn't really matter, but almost all of them denature proteins, and again, not terribly reliable, but they're very useful, at least originally in their antiseptic sense, and historically, they work well because of this. They worked on a lot of things. They were very cost effective, and they worked well in the presence of detergents and organic contaminants. And they do leave a residue, so that was very desirable. And so they were studied, and again, it was the active ingredient in Listerine, all of these types, and the appropriate dilution, which leaves us to two problems. For really the original topical agents that were utilized for staph infections, and in the early days, probably the precursor of MRSA, when we started to see resistive staph infections, was this, which is a compound in the same family called hexachlorophene. And it was when there was absorption, it was causing neurological damage, particularly in children and babies. So they pulled it off the market. And after that, then we encountered triclosan, and triclosan is during your lifetime. Triclosan, if you have somewhere scrawled away in a cupboard someplace at home an old antibiotic pump soap, okay, it might have triclosan in it. Triclosan was taken out of antibacterial soaps. It was the principal ingredient from the time they started, whether it was dial or whatever. It was going to be all the way until maybe the last 5 years. And what we started to see and see articles about was an accumulation in organs of triclosan residue. And eventually they pulled it. And you'll see the next category is the category that we utilize the most in antibacterial soap components now that are coming up. So it's interesting. So it's become very, very much limited. So that's the interesting historical part about it. Uh, I don't know that you're going to encounter them that much. I don't know that You'd have an old bottle that you necessarily would throw it away. Oh my God, freezing it. But it was over time in certain individuals, and it just became became to the attention of the FDA. I think the big deal with that is why it was so useful. And soaps work well with organic contaminants. So stuff on your hands, dirt, grime, grease, whatever you want to call it. This is what we use today. It's a detergent. Okay. There's two different kinds of detergents. There's anionic and cationic. Cationic, positively charged. Remember that? Anionic, a negative ion, negatively charged. Your laundry detergents are typically anionic detergents. And very effective, but you wouldn't want to, they're not nearly as useful on a continual basis on skin. Cationic detergents are. So for years, early on, we knew about these things. And they had, historically, we used merthiolate and iodine and alcohol, okay? And they were very irritating to the skin. And then magically, back when I was a kid, so we're talking about, don't go there. More than 60 years ago. We'll leave it at that. They came out with a substance called Bactine, historically, because it didn't sting. Everybody used it. That's when they started to use these quaternary ammonium salts. And there's another one that you might encounter called Zephyrin, which is in the same category. Now, you go out and go over to China, you go to the antibacterial soap, and you'll see what's in it. It's called benzalkonium chloride. That's this, quaternary ammonium salts. Low toxicity disinfection of food preparation surfaces. So when you walk into the aforementioned Giant Eagle and they have Clorox wipes, they don't have any Clorox in them. Okay? They don't. You want to see Lysol wipes? They don't have any Lysol. Lysol is a phenol. Clorox is a chlorine. They both have you're going to wipe that on your cart and on your hands when you walk in the store. And what do you walk into? The produce department. You start grabbing the fruit. Are you really going to do that? I don't think so. So understand that if you go into a restaurant and in between turns, in other words, somebody gets up out of the table and they re-prep the table and clean it off, they're not using Clorox. They might be using those wipes. Okay, they're using quaternary ammonium salts because they don't have any particular odor or flavor that would put you off. Okay, that's part of it. Okay, charged and uncharged. Well, how do they work? As detergents work, they reduce surface tension. They're with the way they're bonded, they're somewhat bipolar in nature. So they will adhere to the organic materials and be soluble, when they do so, be soluble in the water, which is the way most soaps work. Most hand soaps and things like that work. So aids in the removal along with the mechanical action of let's say washing your hand or running water, dirt, organic material, organism. So negative charge cell surfaces react with membrane, destroys vegetative bacteria, and envelop viruses. Again, very limited in the sense that you're certainly not going to be able to have any effect on endospores or cysts or tuberculosis, but a lot of personal care products. And just like typical betadine, Pseudomonas is resistant to it and can even grow in solutions of it. So that's, there's certain limitations, which you always have to watch out for, particularly in a hospital with these betadine. If you have that it's like you see in the lab when you do stains, that crusty crystallized stuff, that's bad. Okay, that's where it grows. Those types of things. So if you have an older pump soap or something that's starting to get like lots of particulate stuff at where it's getting pumped out, you probably need to clean it off. There's a lot of little do's and don'ts. So quats are a very kind of an interesting category. This is the Nestor PowerPoint, has a nice summary tables on this. Here's benzalkonium chloride and acetylpyridinium chloride. So it gives you some ideas of some of the things that are in it. So it's useful. And I'll go back to the other PowerPoint to complete it as well. I don't do a lot about preservation that are there. These are making things shelf life or shelf stable. They have to be non-toxic. So when you see sodium contains sorbate, sodium sorbate or sodium benzoate or sodium propionate, that's what it means. It contains, these are organic acids, and when you put them in solution, we change from benzoic acid to benzoate. That's just the nomenclature of it from an organic standpoint. Okay, and really, it's what it does. Shelf stability is good. Uh, I think again, you have to be a label reader with a lot of these things to make sure there's no problems. For the longest time, they used nitrates and nitrites in these. Okay, inhibits endospore, stops growth of Clostridium. That's why they used it. This little thing in the smaller print on the bottom. Okay, so they used potassium nitrate, originally called saltpeter, and it's still used a lot in cooking because it retains that pink color. Okay. So it's a lot of in the old days they called it pinking salt that was there. So you see that a lot. Like if you're like I am very fond of corned beef, they utilize that. It's not the Irish, it's the Jewish style corned beef, please. When I was a kid growing up, we had like 60 in New York metropolitan areas. They had 60,000 kosher delicatessens. Now they have 100. It's like corned beef sandwiches like this. You could die for it. That's why my wife and I go to Cleveland to a place called Corky and Lenny's, which is over in the east, it's sort of the northeastern area of Cleveland for a corned beef fix. That's the closest thing to New York corned beef you can get. Just saying. They have my endorsement. So, but just noteworthy about that. So, a lot of times you look for things that are nitrate or like we buy hot dogs, we buy uncured hot dogs, so they don't have the stuff in them. Okay, you just gotta make sure you cook them adequately. That's really, for instance. And then the nugget about refrigeration just slows down the growth, really doesn't do a whole lot. One, some organism can still grow. Freezing, the big problem with freezing, even though it stops the growth, is the ice crystals. And that's why we see freeze drying being more preferred with things that you want to make sure they have them. And this, again, salting or drying, whether you're salting it, whether you're dehydrating it, and effectively what curing is salting and sugaring and adding flavor components. And you're pulling out the water, you're destroying the microorganisms. You're not, a lot of people don't like it because it's not cooked. My wife being one of them. So when we go, we go to, I don't know if you're fans of going to Costco for snacks. Okay, great snacks. Okay, and one time they had smoked salmon, and again, that's a smoked salmon in Jewish parlance is lox, which is cold smoked salmon. It means there's no heat really applied. There's a little smoky flavor that comes from it. I used to, my dad's place of business was next to a smokehouse, and I mean, and she goes, "This is good," and then she looks and goes, "This isn't cooked." I said, "It's cured. It's smoked and cured." She goes, "It's not cooked. This is raw fish. You eat it." I said, "Okay, I'll eat it." No sushi for her. Doesn't know what she's missing. Okay. So staff, halo tolerant. We learned about that before. Okay. So a lot of times they use these combinations of lyophilization, which is freeze drying. You're drying it and you're freezing it simultaneously. It preserves things for a longer period of times. This is, and again, more typos here. I don't know why that C is there. But salmonellosis, dried eggs, and a lot of places use dry eggs. I think you have to be watchful to make sure people have a certain fear associated with that, or with raw eggs. You can go out if you want to spend extra money and buy pasteurized eggs. Effectively, they're pasteurizing the shells. So some people, if you have recipes that call for raw or just coddled eggs, which are undercooked eggs, you can think about that. Worth a note. I have to get the cooking stuff in. It's the unit for it. Okay. So here again, just some of these. This is a chart that you saw before. This is a similar table that you can see associated with halogens or oxidizing. Again, peroxygens, hydrogen peroxide, sporicidal, meaning it is a sterilant in high concentrations, aldehyde, somewhat unstable with increased pH and temperature. Okay. And so the ethylene oxide is is you can see the problems that were associated with that. And that's why no longer do we use them in the office. Again, 45 years ago, you could. Okay, toxicity of phenolics makes them dangerous. Many phenols were banned, and that's, you can see the triclosan. I was right about 5 years ago when that came out. Okay. So again, the chlorhexidine, even though it has a lot of good stuff, hand prepping, surgical scrubs, alcohol, germicidal, non-irritating, etc., uh, could they have some effect? I suppose they could. That are there. The detergents are there, ineffective against tuberculosis. These are naked viruses. We'll get to why those are so problematic. Pseudomonas, which they talked about before, endospores. Again, even some clots were banned in consumer products. So obviously, I'm not familiar with the legislation in 2017. The heavy metal compounds, allergies would certainly be part of it as well, and all that type of stuff. Uh, you'll see a lot of these products are concentrated because they stay longer and you can get the proper ratio. You'll hear a lot about, if you go into this from an environment, and we have a lot of environmental science students who take micro where they learn about things with parts per million and parts per trillion and things like that that are part of it. Contact time is important. The material is important. And this was the chart. This table, and this is what I meant before. When you take a look at what these things are, Lysol and Clorox wipe are quats. That's why they're so safe and they're ubiquitous. Okay, here, disinfecting spray, quats, alcohol, mildew remover, something you're going to use aggressively. Let's say, you would use in a bathroom. Okay, like that. Halogens, strong. Chlorhexidines, contact lens solutions. Now we can see mouthwashes, Purell. The eye drops here, they would use an extraordinarily a small amount of things like that. You got to be very careful. I assume a lot of you have either wear contact lenses. I was never comfortable putting something in my eye. Just I'm scared of it. Okay. Maybe I don't know if I probably didn't share this anecdote. My sister, who's retired now, I'm going to tell you, maybe 15, 17 years ago, she worked for Bausch and Lomb. Bausch and Lomb was the largest maker of ophthalmologicals. It could have whatever the Boston solution was, this contact lens wetting solution. Number one. Bestseller in the United States, not even close. It was made in a plant in North Carolina. They got a fungal infection in there, in that plant. They had never had a health-related problem. 5 people lost eyes. We're not talking about they had to remove the eye. It was a nightmare. Because she's a marketing type representative, that was her bailiwick, the marketing forecaster, trying to predict the future. But she was very good commercial. So she was on the team that was trying to deal with the fallout. They had to get in front of it. I mean, they obviously had to make changes. They assume responsibility, all that type of stuff. Okay. But it doesn't take much, particularly in that, you can imagine what a critical failure in a health-related product, this was a non-prescription product, could mean, much less a prescription product. So it was extraordinary because they'd never had a problem before with that. It doesn't take much in the way of contamination to create, and certainly in the business world, much less in your own health, a catastrophe. So I think that's worth looking at. I haven't looked at this. 34 healthcare or surgical ICU, 24 nurses, 6. Soap and water 620 times. Study was conducted before the onset of maybe change shows how probably realistic. I think we became a lot more cognizant of hand hygiene, but you'll hear this again and again and again. Hand washing, hand washing, hand washing, hand washing. And we get to the last third of the course I dedicate to the diseases. Hand washing, hand washing, hand washing. Because most of them are spread that way. We touch our faces 5,000 to 8,000 times a day. You may not think of it that way, but inadvertently doing this, adjusting that type of stuff, 5,000 to 8,000 times a day. If you get something on your hands, You can either get in your eye, you can inhale it, you can swallow it, and watch it. It's just it's crazy, but I mean I think we probably dealt with that. So that's the last end note for that. And so ends our journey, okay, with methods of control, not including antibiotics, antivirals, antifungals, etc. That comes after viruses. X out of that. X out of that. See what else is going. Uh-huh. Let me look at the genetic stuff. I'm going to see if I have to give you that Nestor PowerPoint, which is their chapter 8 for both that are there. And I'll start with the historical nugget and I'll go back to ours. So, and I have some interesting introductory material. I always am very enthusiastic when I start a new unit. My levels improve. Okay. I just heard this 15 minutes ago. My son, not the one in the Navy, was in Delaware, and they were staying at a Hampton Inn across the river in South Jersey. He was in a training program. He's working for AmeriGas, all those propane things that you view for your grill, the propane stuff. So he's on board with them. They did they were there for a whole week, like from Monday night till night. They had a big test yesterday. It was like a training, so you had to pass a test, certification test. A guy in the hotel who had passed the test from California got so drunk and was smoking so much in a non-smoking hotel that the alarms went off, and he was so drunk he punched a fire marshal who had just passed for the company and was promptly arrested. He goes, I didn't get any sleep. All of a sudden the alarms are going off. I look outside and got some guy against him. The cops got some guy. Oh my God. It's a guy in my class. They can no longer be allowed to have their training people in the hotel. You talk to the trainer. Oh, the message to the world: be careful when you do stuff like that. It's okay to have a good time, but don't go crazy. Truth is stranger than fiction. Barbara McClintock. In my day, the appropriate term today, I'm sure, for this is Native American corn. Okay. We used to call it, forgive me, Indian corn. Okay. And you put, Halloween, Thanksgiving. Well, she must have been fascinated by that. When she looked at the patterns, it was not in a predictable manner. And so she thought that DNA was literally moving in and out of genes and almost creating gene patterns in an irregular way, but identical gene patterns. And as you might, back in 1950, when Watson and Crick, who didn't get the Nobel Prize till 1953, although their work was done in 1948, okay? Skepticism, okay? It got credence, and toward the latter, here she's 81 years old, finally received what she deserved, was a Nobel Prize. And that's part of what we're going to talk about in this unit. It's a phenomenon called transposition. The name that was given to this were transposons, and they were genes, typically with the aid of a plasmid, that could jump from place to place on a genetic strand, okay, in an organism. It could be eukaryotic or prokaryotic, and create these kinds of interesting patterns. Fascinating. So the idea is to establish, in this particular instance, when it comes to our view of microbiological genetics, that in general, okay, there's a lot of ability to change genetically. And I probably told you before, the phenomena that's associated with these things in bacteria called plasmids, and we'll learn about it in this chapter, called conjugation, literally, actually, can change a staphylococcal infection that is treatable with antibiotics to MRSA overnight. Overnight. If one MRSA was introduced or mutated in that population. Under the right circumstances, it could change. So you'll see, for any of you who are going into clinical careers, when someone, I got this antibiotic, it seemed to be working, now it stopped. What happened? Possibly some phenomenon like that. Some kind of mutation that effectively spread throughout the population. It is not easy. Okay? There's so many nuances to this that are there. So it's all descent with modification. This is a very famous illustration of what happens. Here's a bacteria. Let's say it's E. coli. This is the supercoiling of the DNA. It is packed in there so tightly that when the plasma membrane and the cell wall rupture, when it's damaged, when it dies, whatever word you want to use, it explodes out. And explodes out, and these pieces begin to deteriorate. They fragment. Those fragments can be picked up in a variety of ways and go to other organisms. And so you can get a piece of this DNA, let's say it has resistance to an antibiotic, go to another organism. It has some property. And you'll see that. And we've known about this, are you ready? Since the 1920s, before they knew what DNA was. Before Watson and Crick's research. They didn't even know it was DNA, but it turned out it was DNA. Okay, so here's, probably this was E. coli, easy to grow, handful of salts, water, and glucose. That bacterial growth curve, it grows like crazy. Okay, and there's different ways to regulate gene expression. So we're going to see a variety of those things. And the mechanisms are this: mutation. And mutation has a very, very simple definition: an alteration in DNA. For those of you who are unfortunate enough to be stuck with me for AP1, and we did the cell cycle, you'll remember, prophase, metaphase, anaphase, telophase, cytokinesis. Okay? Somewhere in S phase, as I like to say, kissed by S phase. Okay? And it's the same, you'll probably see the question again. Okay? Where do mutations occur? In S phase, because that's where the DNA was synthesized. That's the idea. So alterations, the fact that it's a mutation doesn't mean, that if you have a mutation or I have a mutation, then all of a sudden we're going to have a third eye. That would be useful. You really have some interesting designer glasses. Okay? Mutation just means an error in DNA. The question is whether or not it's expressed, and if it is expressed, what does it actually do? So there's a lot of variations to the term mutation that are there. When we're going to be looking at this population and things like MRSA, okay, we're looking at effectively mutations that have occurred that effectively were Darwinian, if you will. It was an evolution to be able to combat a constant and chronic exposure to antibiotics of a certain type. And so they began to develop means to fight off the antibiotics. That's kind of the thing we explore a bit in this chapter. Resistance, and we explore it again in the antibiotics chapter. And then this is the interesting part about the changes that can occur overnight. Horizontal gene transfer. We don't do that. Not normally. We do vertical gene transfer. Parent to child. Mom and dad get together, or whoever mom and dad is get together. And the reason I say that is because I have 3 adoptive children. So genetics are of interest, but when my kids get to, give us your family history, they just on the chart. Don't know. They don't have a whole lot of information. So vertical transfer, mom and dad producing offspring, 1, 2, how many ever, and they're going to get genetic components from each one. That's vertical. Horizontal means same generation. And it's saying, I always use the same example. It's like if someone who's very athletic is sitting over there, they can touch the person next to them, and they touch the person next to them throughout the entire room. And by the end of them touching each other in the couple of minutes it would take, all of us would be equally athletic. So my half-inch vertical leap might improve. That was it. If Tiger Woods could do that, I could be a great golfer. That was always my prayer. One day. So vertical versus horizontal. We're going to see four major means of horizontal gene transfer. One you saw before earlier, transposition, another one called transformation, another one called transduction, another one called conjugation. And so they're just showing you some of these genetic changes versus a spontaneous mutation, and they occur all the time. You and I make, I don't know, every day at least 1 billion cells. Probably in our gut alone, we make 1 billion cells in lining cells that are being used constantly. Okay. Even under the best of circumstances, occasional mistakes are made. Most of those cells, A, have a very short lifespan. B, we have defense mechanisms to combat them. C, they don't really affect us. They're just one in an array of billions upon billions of cells. Okay, but spontaneous mutations, and I'll give you some of the numbers as we move on with this idea that occur. Spontaneous mutations occur. Now, that, and typically if they stay where they're supposed to, if the mutation is there and isn't corrected by a variety of means, it ends up being transferred. Versus here, we can see a plasmid, once it's transferred, all of a sudden now, it'll be transferred horizontally in the same generation. So again, it's like you could magically change some ability. Oh, you had glasses, you don't need glasses. Okay. Anything like that. You had, maybe I could grow hair back again. Don't start. You can only hope. So those are the kinds of things that are there. And once it becomes established, then theoretically you could pass on that trait. What we do today in an effort to try to do this kind of variation of horizontal gene transfer is something I commented on before. It's called gene therapy. It's really in its infancy, and it's utilizing at least for now, a retrovirus a la the HIV virus, actually taking that virus, and we explore that in the viral chapter and look at how that will attempt to resequence certain cells' DNA. That's the idea. So that's a technology that is evolving, and over time, I assume that'll be part of it. So you're familiar with these terms, okay? Genotype versus phenotype. Genotype is the actual genetic makeup, sequence of nucleotides, and we'll get to the haploid and the diploid versus that in a second. And changes in genotype, if we have observable or measurable phenomena, they're called phenotype. And yes, in environmental conditions play a role in that. Let's look at the big differences between these things. So, if you were in a prokaryote, typically we see mutations occur about 1 in, let's say, around 10,000, probably to around maybe 1 in arbitrarily about 10 million. In our cells, probably 1 in maybe, let's say, 100 million. It's 1 in, let's say, 1 trillion without going all those years. A big difference. The rate of mutation in eukaryotic cells is considerably smaller than in prokaryotic cells. Okay? These are classified as spontaneous mutations, just errors in DNA that occur through the natural part. It's tough to assemble a complex strand of bases accurately all the time. Okay? Be tough to do. You can only imagine, because the strands are just millions and millions of bases long. Versus what the change is this, induced mutations. Induced mutations means exposure typically to one of two things: radiation or chemicals. When that occurs, typically it increases the rate by a factor of 1,000 times. So when we expose, and antibiotics, everybody, are chemicals, a bacteria, we're increasing, even though we're killing it, we're also increasing the rate it's likely to mutate. And if you look up here, you could increase this number to 1 out of 10. To maybe 1 in 10,000. It's like, we're talking about 10 to the minus 1, 10 to the minus 4. It's about the range. That's a lot of mutations that occur. And so it's very, very much, you will see over time, it's a numbers game. Why is that the case? To me, there are 3 basic factors that play a role. Understand, everybody, DNA is DNA. So the genetic code, that chart that you've all seen a bunch of times with the A's, the U's, the C's, you remember that? It's got the other side, I don't want to draw it. It's got the 64 of those things. That's the same for both. Inherently, that has a lot of built-in. Most amino acids that form those proteins have at least 2, codes, duplicate. Some as many as 6. Most of them have 4. You have limited punctuation. You have 1 start code and 3 stop. So at least 60 of those codes code for the 20 amino acids. So inherently, the system is pretty useful to start. And typically, if you get the first 2 letters right, you're golden. You guys would do great on tests. If you get just 2 out of 3, that would be 100. Happened. Okay. So the genetic code is there, and DNA is DNA. So that's not a difference between the DNA. But let's look at the DNA. We have on the prokaryotic side versus the eukaryotic side, we've got a single circle. It's a big ass circle. All right. We're recording. Versus pairs, linear pairs. So, but items like that, inherently, what this means is this prokaryote are inherently haploid. On top of that, that DNA is ready to go to replicate at all times. So it's already supercoiled. You can see the chromosomes. Versus here, linear pairs, diploid, big deal. Okay. And it's in the form of chromatin, so it has a certain amount of controls that are there with those histone proteins you might recall. So that's the first difference. So what happens, and we even have different names. Remember, it's the origin of plants. So when you see a typical plant, let's say roses are probably because they played around with colors. But let's say typical roses originally were red. Let's say that was we call the wild type. That's the name we use for bacteria. A non-mutated bacteria is a wild type. Anything else that's a variation is a mutation. So you either have mutations or you don't. So the only 2 ways it can be, typically for bacteria, are the wild type, the stuff that we see most commonly in the environment, versus a mutant. Because with that single strand of DNA in a circle, wherever, remember, it's double-stranded DNA in the sense. When I say single strand, it's a single circle of DNA. They're both the same kind of DNA, double strand. You see, when you get the viruses, we have some oddballs like single-stranded DNA and double-stranded RNA. And I don't really delve into that too much because I think it's just sort of being. But effectively, when there's a mutation anywhere, it's a mutation. Okay. Typically, it's going to cause some type of alteration, likely in its phenotype. With our pairs of DNA, it's different. We're divided in each segment, just like the circle is divided into genes, genetic loci, genetic locations. But They can be one of two types because they're the same. They can either be dominant or recessive, recessive or dominant, dominant or dominant, recessive or recessive, right? Remember that? Punnett squares, all that good stuff. All those neat things, dangling earlobes, hitchhiker's thumb drive. Freckles or not freckles. Hair on your. They're there. So what happens if it's dominant and recessive? Only the dominant strand is expressed. Inherently, only if there is a mutation on the dominant strand here or here. If it's on the recessive strand, it doesn't matter. If they're both dominant or both recessive, they only express one side. Okay? So if it's on the side that isn't expressed, it doesn't matter. It's inherently less likely. That's where the numbers come. That's one. The distinction between the DNA. Distinction number 2. I didn't do a lot of this. They show you it on this PowerPoint. Called messenger RNA process. Messenger RNA processing, if you recall, and prokaryote don't do it. Eukaryote do. So effectively, here's a strand of DNA. Here's a strand of messenger RNA. That's very famously transcription. In bacteria, prokaryotic organism, that messenger RNA makes proteins. Business done. So there's a mutation here. It alters the messenger RNA. It may very well alter the protein. We'll go into ones that do and ones that don't. In our cells, in eukarya, different. It doesn't make DNA, it makes what's called pre-messenger RNA. That strand of pre-messenger RNA, I'll draw it again, has alternating sequences called introns and exons. What happens in the processing is that only the exons are expressed. So you get a little piece here, and a little piece here, and a little piece here of these exons, and then effectively they're stapled together. So the actual messenger RNA or processed messenger RNA is considerably smaller. They used to call the introns and things junk DNA. They're really more regulatory DNA. We only express our variation between you and I with a couple % of our DNA. You know, why I'm, don't have as much hair as you do. Yet, for you guys, yet. Just saying. Number 2, first, circles of DNA versus DNA in pairs. Second, messenger RNA processing. Last, magic. Eukaryotic cells have this enzyme, DNA polymerase 3. It's all living things have DNA repair mechanisms. And in fact, when it repairs DNA, it's not matched. If you have an A and a T, it's matched. If you have a T and an A, it's matched. If you have a C and a C, not matched. So it's missing in a G, right? A's and T's, C's and G's. Mismatch repair is the enzyme. It's a form of DNA polymerase that we see in prokaryote. So when it basically is surveilling and it gets to a mismatch, it's as likely to remove the right strand versus the wrong strand. It's a 50-50 shot. Okay, mismatch repair is as likely to remove the strand that should be there as the strand that's not there. DNA polymerase 3 is much more likely to remove true mutation. Voila. That's the third major mechanism. why our DNA is less likely to be problematic than their DNA. Okay? So those are the three major reasons. And so what happens, then we get into the next level is whether or not it's expressed. Okay? So it's like anything else. So if we go back to that pre-messenger RNA, if it's and if the mutation is here, pre-messenger RNA doesn't really exist in bacteria. It immediately makes the protein. So the mutation is here and it's here. It's always going to be expressed. So it also, and it depends on where it's expressed. It's nothing more than a strand of amino acids. If it's on if it happens to be a mutation or an error, and the first two letters aren't affected, okay, most likely it's not going to affect the eventual thing. So if the mutation is there and it doesn't have any impact, we have a great term for it, silent. Tree, bars, nobody hears, that thing. Next, what happens if it alters an amino acid? Okay, if you alter an amino acid, for the most part, you alter what the protein is going to do to some extent. Sometimes it can be drastic, sometimes it can be minor. Sometimes it can have really a negligible effect. But we call that because you alter the sense, as they refer to it. You missense mutation. That's not going to be really bad. Sickle cell hemoglobin, by the way, one amino acid. Now, if you prematurely encounter a stop code, and we see this with certain kinds of mutations, which are called additions and deletions. Point mutations or isolated mutation, not as bad. Then it makes the protein not really work, and it's called very famously nonsense. And you'll see some illustrations in these PowerPoints of missense, silent missense, and nonsense mutation. The Cowan textbook used to have a great, because it's three-letter words. It would be like, and they had like a little thing that said, the fat cat did, not something. And then if you altered it, it would be the fit cat. The cat went to the gym, the cat worked out, the cat was being careful. And then, it would be, then if you had one of these oddball ones, it would be the fat, cow. What the hell's going on here? And that would effectively be, that was the distinction between a silent mutation, a missense mutation. And that's on like an old version of this that I used to have, but I can't access when I taught at a different school. But I digress. It's probably saved somewhere. I have like a portable hard drive. Some places probably got that. I'll have to find. All right. Good enough. See you later. Goodbye. Have a great weekend. And for old time's sake, as I love to say, have fun storming the castle. Fun storming the castle.